Welcome to our last section of Chapter 1, Section 1.9. We're going to continue to build on talking about linear transformations by talking about how we can find the actual matrix and some other information about linear transformations. So first, I'm going to introduce something called a standard basis. It's actually a preface for Chapter 4. Just do an example of how we can find a matrix, and then we'll talk a little more about onto one-to-one, and have a final thought on transformations. So let's start off with talking about what is the standards basis. Well, if you have the basis of a vector space, let's just talk about basis in general. Let's say Rn, because we haven't gotten what a vector space is a set of linearly independent vectors who span that space. So again, two properties, they're linearly independent and they span that space. These can be looked at as the building blocks, kind of like the DNA or however you want to look at it. The base, they're the basis because they are the building blocks of everything else. Chapter 4 is where we're really going to go into much more about, is something a basis and what is a vector space? There's a lot more into that, but we're going to start with just basically Rn. So we have real numbers, n dimensions. Now the standard, what's called the standard basis, is a set of vectors that we label E1 through En. E stands for elementary, by the way, where EI is a 1 in the ith component and 0 otherwise. So for example, if I have R4, and I'll do an example, and I'll write this out nice and pretty in a second, but if I had R4, so I'm going to make that note, R4, so we have components. So that would mean that E1, what I would do is I'd put a 1 in the first spot and a 0 because I have 3 components. On the other hand, let's just jump to E3. What that would be is a 1 in the third spot and a 0 everywhere else. So hopefully you get the idea about how we can build this. Now, a couple quick notes about that. So this would look like for R4, it would be these 3. Again, these would be E1, E2, E3, and E4. But, and this is really important, is that for 2 and 3 dimensions, some of you may be familiar with what are called IJK. Sometimes even in Calc 3 they do that. It's really only used by engineering physicists. Mathematicians really don't do that because that doesn't make any sense if you're going to go to higher dimensions, you got to throw that out and switch over to E. So why not just be consistent and use these E's everywhere? So in our class, we're going to focus on the E vectors. But if you wanted to do, if you're an engineer or a physicist, you may see those as IJK. Again, I don't recommend that because then how do you correlate that versus the imaginary number and J, and there's lots of other things that this can get super confusing. So I prefer the E terminology. I find it just as much simpler. Now, there's a really cool theorem about using those elementary or the standard basis. And that is if I want to do a linear transformation, the matrix, because remember, if there's linear transformation, then there is a matrix that corresponds to that linear transformation. And the interesting part is we simply, so I'm gonna put this out, to the first column, I simply take E1 and I say, okay, where does that go? Oh, and whatever that, pardon me, where that new matrix, wherever that new vector is, that's what ends up going into the first column. We take E2, where does that go, and so forth. And that gives us all of our information. So this is actually then called the standard matrix, standard basis, standard matrix for linear transformation. Again, there is potentially multiple, you can look at it different ways, but notice it is always going to be unique. So it's called the standard matrix because it's based on a standard thing. So again, this is unique and it's going to help us understand this a little better. Now, let's do an example about how we can actually use that theorem to kind of make this a little more clear. So suppose that I'm trying to do a dilation. So remember, that just means you take every vector and I'm going to expand it and make it bigger, so to speak. So what I would do is I'm just going to take R3 to R3 because I'm not changing the dimensions. And so I can look at this as E1 is just 5 times E1, which is 500. Similarly, the transformation of E2 will end up going to 050. And as you can probably guess, the last E3 would go to 005 because it's just 5 times 0. Well, the only thing that's not 0 is the 1, which turns into a 5. So that's really easy. So putting these three vectors together, our matrix, our standard matrix is 5s on the diagonal and 0s everywhere else. That seems to make perfect sense. And that was actually really simple. Well, let's talk about what's called a rotation. So I'm going to rotate this clockwise, radians. Oh, wait, this is trigonometry. Oh, okay, so this is all going to come back. So again, we're going to build on stuff you've learned in past classes. It's just, that's the way math is. Math is like a language. We build on stuff. So what I'm going to do essentially is I'm going to rotate down. Everything's going to rotate on this circle pi 6. So what initially was here, which by the way would be the vector 1, 0, that's going to go to whatever this new vector is right here. And so we got to figure that out. And the way we can actually do this is by transforming that by using cosine. So as a reminder, there should be a break right there. This cosine always corresponds to the x value, and sine corresponds to the y value in R2. That's a basic thing you should learn in trigonometry class, and then you use probably in multiple times in calculus, because this is how we use trigonometry. And it's radians, not degrees, radians. So cosine of negative pi 6 is square root of 3 over 2. Cosine of sine of negative pi 6 is negative 1/2. Again, these are basic angles. You should have the hang of them from your classes. So where does E2 go then? Well, think about what your starting matrix is. Well, that would be cosine of pi thirds. Well, why pi thirds? Well, if you look at a circle, so my original thing, which was right here, a way to think about this, that value right there is cosine of 0, sine of 0. And then I shifted them down. So that's why we came over this. This originally was right here because it was the vector, because E2, as a reminder, is 0, 1, which I'm going to try to write this in, is cosine pi halves, sine of pi halves. Wait, if I subtract pi 6 from each of those angles, we get pi thirds. We compute this and boom, we got this. So these two vectors right here and right here form our new matrix A by just plugging them in. And now if we multiply them by any vector in R2, it rotates exactly pi 6 radians. That matrix right there, super powerful in that regard. All right, so let's talk about some more examples. Well, just go to your textbook. I'm not going to hound on this. This isn't going to be a huge thing. This has lots of values in certain applications, especially if you're designing CAD programs, if you're designing various things where you want to rotate them and look at them in different forms. But go ahead and look at your textbook. It has lots more examples. I'm not going to give you a ton of homework on it. It really is very simple. And I don't want to, well, not simple, but it's just something that you got to practice to start getting. But it goes back to, where does E1 go? Oh, if I'm rotating it, am I shifting it? Where am I going with it? Now, let me make some comments about onto and one-to-one. You've all probably heard those terms because they should have been taught in your algebra classes. If you took discrete math, it's probably in your calculus, because these are key things about functions. So as a reminder, a function is onto if for every B in the codomain, Rm is the image of at least one element in Rn. What does that mean? Here's another way to think about that. That literally means that the range equals the codomain. So the codomain is everything I'm going to play in, and then the range is as such. Now, the problem about showing that equality is actually extremely difficult because our codomains are infinitely big and there's lots of horrible things. So instead, we use this fact. We're trying to find at least one X that would satisfy it. Similarly, 1-to-1 means that for every B in the codomain, there's at most, meaning that doesn't mean that there is one for every B value, but it means that if there is one, there's only one. Okay, now let's do a quick example. This is linear transformation. And I gave you the matrix. Cool part, by the way, sorry, in row echelon form. So what are the domain and codomain? Well, the domain is going to be R2, since I can only use vectors with 2 components in them to multiply this by. And that would give me a vector with 3 components. So it's R3 is my codomain. Next is the question, does T map onto? Now the key word here is, I'm using this terminology because it's similar to how my math lab likes it. Onto just means, am I, so to speak, you can think of it this way, am I going to hit every single thing in R3? So in other words, if I made an augmented matrix, I'm just going to write this right here. Suppose I made an augmented matrix. Now this is how we check if something is in the range. We make an augmented matrix, we make A, B, and C. Well, essentially what I'm saying is, can I use any A, B, and C and will this work, or are there limitations? If you notice, this last line has a major limitation. C cannot be anything besides 0, or else it doesn't have a solution. And in fact, because we're already in row echelon form, we already know that for any B where I don't care what, but that last term is not 0, then the system is inconsistent, so there's no solution. Therefore, it is not onto. All right, but is it 1-to-1? Well, again, the way we look at this is there are no free variables. So I have 2 columns and 2 pivots, which means I have no free variables, which means it is 1-to-1. But guess what? If you have a free variable, it is not 1-to-1. So that's actually one of the cool parts. This row echelon form of a matrix, you don't need to go reduced row echelon, just row echelon form gives you so much information. So that is why we care about it. Now, finally, here's a couple other things that people use. If I have a linear transformation, that transformation is 1-to-1 if and only if the only solution to the homogeneous is the trivial solution. If you have any of the others, remember, those come with free variables. So we can simply look at the homogeneous situation. Similarly, if I have a linear transformation and its standard matrix is A, then it's onto if and only if the columns of A span, or in other words, the columns, I can hit every possible, their linear combination is going to create all of Rm. And T, so we can go back, by the way, to our spanning and definitions of that. Again, we'll utilize this a lot more in chapter 4. And then also, T is 1-to-1 if and only if the columns are linearly independent. Hey, this is really nice. This actually tells us lots of information and helps us understand this. One final thought, and this is something, suppose that I gave you a linear transformation where T goes to some vector, T takes V to W. Does there necessarily exist a linear transformation from W back to V? Does it always happen? If it doesn't always happen, what conditions are necessary? These are some of the questions that can be asked as we take linear algebra much further and talk about other applications of it. All right, that's the end of this video. Good luck. Please let me know what questions you have.